Everyone, we will conduct the experiment on light, that is the laser light. We are going to find out the wavelength of a given light, that is laser will be given, its wavelength we have to find out by the diffraction experiment. So aim of the experiment is to find out the wavelength of a given laser source by diffraction grating. Given apparatus are diffraction grating, laser source, screen, stand and other apparatus. This is the laser source or PN junction or semiconductor laser it is. Semiconductor laser or we can say PN junction laser. So here we should take very precaution that we should not look at this laser beam. Okay, otherwise it will damage our retina. This is one care we should take. We should not look at the beam which is coming out from this point. And this is the laser grating. That means this is made up of a glass, quartz glass. Quartz is a kind of a glass, and here we have a fine lines on this which are made by the diamond tips. Fine lines they have made on this. The lines are 250 lines per inch. This is called as laser grating. So here they have made a lines because that line indicates the opaque, which makes the opaque of a glass, and where there is a no line, it is a transparent for the light. So in this way we will be having so many slits, and so many slits are together are called as the laser grating, which bends the light. Okay, when light is passed through this grating, then it undergoes the diffraction, that is bending of the light. And this is the holder for that. I'll just initially we have to fix the distance between this grating and the screen. Let us fix, for example, 80 centimeters for the first reading. So let us take this as a 0 over here. So this is, there is a marking, and this is 0, and 80 centimeters, let us adjust to this graph sheet. Fine, this is the screen. On the screen we have to fix the graph paper to measure the distances between these points. When I take this grating in between the path of this laser beam, I will get the diffraction grating. Okay, so this is the initial light beam. When we keep the diffraction grating in between the path of a light, at that time the light will diffract and we will get the diffraction patterns like this. So whereas this point is central maxima, this first point is first order diffraction, this is second order diffraction, this is third order diffraction, and so on till the nth order diffractions will take place. Similarly, towards left hand side, first order, second order, third order and fourth order diffraction will take place. So now what we should do is we have to mark these points. We should take a sharp tip pencil and then carefully at the center we should mark this central maxima. And this is first order diffraction point. Similarly, second point, third point. Same thing we should do with respect to left hand side, first point, second point and third point as third order diffraction patterns. So this readings is for one distance, that is D1, distance between screen and the slit. Now we should increase the distance between this and the screen, or we can decrease also. I will increase this to 100 centimeters. Let me increase this to 100 centimeters. So this is the 100 centimeters. Okay, and again we should attach this to the another position. We should attach this screen to the another position so that we can take the readings for D2 100 centimeters. Same thing we should repeat here. This is central maxima. Make a point over there with a sharp tip pencil. First point, first order, second point, second order, third point, third order, and this is nth order we don't want. We need only 3 readings towards left and towards right. This is first point, second point and third point. Okay. After that, we should remove this carefully. This is the schematic diagram of this diffraction. Here we have a laser source. This is the diffraction grating. When light passes through this diffraction grating, what happens is the bending of light takes place. This is central maxima. This is first order, second order diffraction beam. Similarly towards right hand side, that is other hand. And here we have this distance d, that is distance between diffraction grating and the screen. Okay, and on the graph sheet what we have measured is this distance from this central maxima to this point 1, central maxima to the point 2, that is second order diffraction grating. This distance we need. Okay, so that what happens is here we have the triangle formed, that is this is a base, this is opposite side and this is hypotenuse. Okay, from this we can find out the tan theta. Okay, so we can find out the tan theta. What is the tan theta? That is opposite divided by the adjacent. From this tan theta I can easily find out what is theta. Theta is equal to tan inverse of this ratio, opposite divided by hypotenuse, that we are going to find out from the tabular column. These are the markings which we have taken in the experiment. This is central maxima. Okay, you can give even the line to this. Instead of point you can give line also. So I have taken the points over here. This is central maxima. This is first order beam at the point which we have taken marked. This is second and this is third order diffraction pattern. Okay, so now we have to measure the distance between the central maxima, this is a central maxima, to the first order. What is the distance between this point and this point? The second reading will be the difference between the distance between this point to this second order, and the third reading will be from the center to the third point. So we should take the readings with respect to center. Similarly towards the left hand side, I have taken readings and noted down over here. This is the tabular column. The first column is the distance between grating and the screen. First D1 we have taken as 80 centimeters, that I have written here in the centimeters. Second column is order, first order, second and third order diffractions, and the third column is distance between the mth order and the maxima, that is the first, second or third to the central maxima. Left side readings, that is central maxima to the first order, that is I have taken it as 0.5 centimeters. On either side it is same. And second point to the central maxima, 1.1 centimeters we got, and third reading I got 1.6 centimeters, that is the distance between center to the third point. Similarly, the second set of readings I have taken to the distance D2 is equal to 100 centimeters, and we have these three orders. Okay, and the next column comes, it is xm is equal to mean of these two, that is L plus R divided by 2, and we need to calculate all the means of these orders. Then the theta m, that is tan inverse of x divided by d, where xm is this value, d is this value. Okay, and we should calculate that. When I take the sine theta and it's, when I substitute the value in this lambda, I am going to get the readings over here and calculate the values. The mean will be the final answer, that is the wavelength of the light. Here we have observations. Number of lines per inch, n is equal to 250. That grating constant d is given as 2.54 divided by n, that is conversion to the centimeters. Okay, that we should do it, and this is the formula. Lambda is equal to d sine theta divided by n, where n is the order, first, second or third. Okay, then we are going to get the reading in angstrom. So final reading you are going to write here, and that will be the end of the experiment. what we found is the wavelength of given light